Hey guys, here is our notes for Inclines 2, two objects with an incline. And so for problems like these are basically some modified Atwood's machines. And so we use a lot of the same principles about how they work using either the unfolding method or once again using the method where you substitute back in. So what I'll probably do with this one is I'll use the unfolding method when we're talking about how to solve these kinds of questions. So we have here two masses attached by a rope over a frictionless pulley. The incline is frictionless, so there's no friction on M2. And figure out what the acceleration of the masses is, R, and then figure out what the tension in the rope is connecting those two guys. So first thing I'm going to do is I want to use the free body diagram for each one of these. For the first block, I have this FG1 in tension. For the second one, this is where I'm going to have to use the way we take this apart. Let's call this FG2. Normal force is perpendicular to the surface. Looks like tension still goes up the ramp. And then for this one, it looks like the FG parallel is going to go down this way. And then the perpendicular piece will be down there at the bottom. Okay. And so once again, there's no friction on the thing. So we know that the tension and the parallel blue force are the only things acting on it. And for the acceleration, we need to figure out what A is, obviously. So using the free body diagram of the first one, we have this tension minus Fg1 equals M1A, right? We're using Newton's second law. Sum of forces in the x direction is mass times acceleration in the x direction. Well, what we have here is there's kind of a problem. We don't know which way the mass is going, okay? So kind of go down here to the bottom notes here. So which way will they accelerate? So once again, in the obvious problems, the earlier problems is pretty obvious. The bigger mass won, which means that it would accelerate towards that side. But in this one, it's not always the case, right? So we have a block that's hanging here, and then we have a block sitting on the incline. We have that, right? So for the first block, just hitting down, it is the FG1 or M1G. So in this case, it would be 4 times 9.8, which is about 39.2 newtons. And compare that with the force of the other one. So it's FG parallel, that's the piece pushing down the plane, which in this case would be mg sine theta. So I plug everything in for that second mass, it'll be 6 times gravity, which is 9.8 times sine 30, which in this case would give me 29.4 newtons. And so what happens is when I look at this thing here, that this downward force here is greater than that weight, this FG parallel piece going down this way. So what that tells us is the acceleration is going that way. So the object is sliding up the ramp and M1 is traveling downward. So using the unfolding method, we can use our Newton's second law to figure this out. So we would do something like this. Negative Fg1, it's pointing to the left, plus tension, minus tension. So now I'm using this guy right here. So it'll be minus tension, that's going to the left, plus FG parallel going to the right. And that will be the total acceleration of the total system. So we can see here the tensions cancel. So let's clean this up just a little bit. We have FG parallel minus FG1 equals M1, M2 times A. So we can start plugging these in. This FG parallel is going to be M2G, looks like that's sine theta. That's this guy down here, minus M1G. And so the rest of this is just doing the algebra to plug these guys in. The M2G sine theta, we already know this, that's 29.4. The M1G, that's 39.2. Four and 6 for the two masses. So we get something about negative 0.98 meters per second squared. Or, there's another kind of weird way to say this. It's accelerating up the ramp for mass 2, and mass 1 is accelerating in the downward direction. And so you kind of have to understand which one we're talking about. The way we ask the question, the acceleration of the masses, we tend to want to use the magnitude of this value here. So we would say the acceleration of the masses is about 0.98 meters per second squared, and then you would have to indicate whether you're talking about up the ramp for mass 2 or downward for mass 1. The other thing we have to look at is we have to figure out what the tension in the rope is. And so once we do that, we can utilize this equation that we started off with up here. Once you know the acceleration, you just plug everything in. Tension minus the FG1, so we know this value down here is 39.2, equals M1, which is the 4, times the acceleration. So here we'll have this 0.98. Because we're using mass 1, we have to use the negative of this because it's going downward, which means tension becomes about 35 newtons in the string connecting the two ropes. Okay, so once again, for this, you have to, when we start looking at these, we have to sit down and we have to figure out which way the which way the objects are accelerating, because then our signs will be a little messed up. In other words, we might get a negative symbol in here when we subtract the masses when that's not appropriate, okay? So you have to understand which side would quote unquote win and which side loses. In other words, which way is it going to go in terms of the acceleration? So same kind of question, only this case we will now have some friction involved. So in the name of physics, a monkey is attached to a sleeping sheep on a ramp. And as we all know, the coefficient of friction for a sleeping sheep on a ramp is precisely 0.15. So let's first determine the acceleration of the system. So what we have to do first is we have to understand which way it's accelerating. So doing that, we'll use the monkey over here. Let's call this mass 1 and we'll call this mass 2. So we'll have FG1 here, and then we'll have tension. For the sheep, we have FG2. We have its normal force, tension directed up the ramp. Looks like we'll have the parallel component and then the perpendicular component with the angle of the incline here. For the FG parallel, we know that is going to be FG sine theta. And for the perpendicular side, looks like it'll be FG cosine theta. So we have to figure out who wins. In other words, which way is it accelerating? So let's figure out what FG1 is. It is M1G, which turns into about 235.2 newtons. And then we have to figure out what the FG sine theta is, or the parallel component here. So this is going to be M2G sine theta, which is about 176.4 newtons. So it looks like this guy wins the race. So that tells me that the acceleration is going down for the monkey and up for the sheep. So acceleration is down this way and up the ramp this way for the sheep. So instead of using the unfolding method on this way, we're going to use the other method. Oh, forgot to add the friction, right? Since it's being pulled up, the friction force, let's add this gold color. It's gonna have to be pointed down this way. We'll call that F sub F this way. So since it wants to accelerate up the ramp, we have the friction pointing down. So let's do Newton's second law using the adorable monkey first. So it looks like the adorable monkey has a tension going up minus the FG1 going down. And we're gonna go M1 times negative A because I know it's accelerating in a downward direction. So we can fill in as much of this as we can. Giving me tension minus, let's see, 24 times 9.8 should be about 235. We just figured that out. Equals negative 24 times A, right? So there's our first equation we're gonna get to use there. Now let's do, so this was for the monkey. For the sheep, we can do the same thing. We can utilize the fact that up the ramp was positive and down the ramp was negative using this method. So up the ramp positive, it'll be tension. Friction points down the ramp. The FG parallel points down the ramp. And so this is going to be M2 times A, positive A because it's accelerating up the ramp. Notice we have friction here. So we're going to go mu times the normal force. We'll go ahead and break this apart here, this parallel piece to be M2G sine theta. We need to know what this normal force is. And so we look at the y direction and notice that the normal force, pointing up, sorry, wrong pen. The normal force is equal to the FG perpendicular. So the normal force is M2G cosine theta, which should be 28 times 9.8 times cosine of 40. So we get a normal force of about 210.2 newtons. And then I have enough information to plug everything in. So tension minus the coefficient of friction, which was 0.15, times 210.2, there's the normal force. My M2G sine theta would be 176.4 from above in the green here. equals the second mass, which is 28 kilograms times his acceleration. Cleaning this up a little bit, we get tension minus 207.93 equals 28A. And what we do is we get this value here, and we plug it into this guy here. So for me, I would kind of do it like this: 28A plus 207.93. So 28A plus 207.93 minus 235.2 equals negative 24A. Do a little bit of number crunching and you should get an A value of negative 6.8, just call it 2 meters per second squared. So once again, for the monkey, he's accelerating downward. For the sheep, he's accelerating up the ramp. So let's be sure to indicate which way he's going. And if we can draw an arrow that matches the diagram, that works out pretty well. So now that we know the acceleration of the system, we can go back and use either one of these two equations to figure out what the tension in the rope is. I think I'm going to use this value right here, simply because it seems to be less complicated than the others. So for the tension, we'll get something that looks like this: tension minus FG1 equals, let's see, negative M1A. So when you plug all it in, you should get about 398.8 newtons of tension in the string. Cool. So to recap real quick, we have this idea of two objects that are connected. So the object on the left is just a hanging mass, and it's going to have its weight and its tension. For the thing on the right, that's going to represent the object on the incline. It'll have its normal force, there's its tension. It'll have the parallel force, and then the perpendicular force. If there's friction, depending on which way the object is accelerating, friction will go one way or the other. So it just kind of depends on where it's going. And we determine that by figuring out which one is greater. Is the hanging mass, or the force of the hanging mass, greater than, less than, or equal to the FG parallel piece, right? So we compare the mg with the mg cosine theta. And so I guess we would have to indicate the first and the second. And so these values tell me which way the object will be accelerating. Up the ramp, down the ramp, or there's no acceleration, so it could be sliding at a constant velocity, or it could be at rest. So that's a lot of information. These questions do take a lot of effort, and so we're going to slow down and work on these for today and Wednesday. Let me know if you guys have any questions. Thanks for watching. Bye.